casa de la bachata. La, 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 la. La casa del merengue. La, 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 la. Y la casa de la bachata. Casa de la bachata. Música, 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 te traigo música, 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 música de la República. Ajá.
Hello, everybody. My name is Sydney Winston. I am an atheist activist out of Vancouver, Canada. My goal is to create atheists, where everybody who is not an atheist becomes one by adjusting and correcting their thinking in a realistic world that we live in today. Today we're going to go to science school on elementary particles. It's something that the Christians have a hard time grasping the concept of what these things are. So this is as much for science enthusiasts as it is for Christians. You will learn something. There are 14 little clips, couple of minutes long each, and by the end you will know about as much about elementary particles as there is to know. So what I suggest we do is get to it.
Hello, and welcome to our segment on elementary particles. An elementary particle is a particle that has no internal parts. In other words, it's a particle that has no other more elementary particles inside of it. We've seen two of those so far, the electron and the photon. In the last segment, scientists were reducing the 92 elements that made up all of matter down to three particles, the electron, the proton, and the neutron. In this segment, scientists went to the mountaintops and put bubble chambers up in balloons to find a vast array of new particles. We'll cover those particles in this segment. We'll also probe the proton, much like Rutherford was able to probe the atom. He found a nucleus inside. We're going to find some things inside the proton. But first, let's take a look at the particles that were found from cosmic rays. The Earth is constantly bombarded by radiation from outer space, called cosmic rays. These cosmic rays are made up mostly of high-energy protons and high-energy photons called gamma rays. Cosmic rays collide with atoms in our atmosphere, generating particle chain reactions that continue all the way down to the surface. In our first segment on the Milky Way, in the How Far Away Is It video book, we noted cosmic rays are produced in supernova, like the one that created the Crab Nebula. Gamma ray bursts are the most energetic and luminous electromagnetic events in the universe. They can release more energy in 10 seconds than our sun will emit in its entire 10 billion year expected lifetime. It is the very high energy of the deep space cosmic rays that have the power to smash into electrons, protons, and neutrons in the atmosphere, creating a wide variety of previously unknown particles. Charles Thomson Rees Wilson invented the cloud chamber in 1911 to detect these particles. So physicists climbed mountains like this one that Wilson used and went up in balloons with their cloud chambers hunting for new particles. Here's what it looks like when charged particles pass through a cloud chamber. The chamber contains a vapor of alcohol placed inside a magnetic field. When charged particles move through the chamber, they cause little droplets to form. These are the cloud tracks that we see. It works on the same principle as tracks forming behind high-flying jet aircraft. Here's what cosmic rays look like in a cloud chamber. These rays are penetrating multiple brass plates, each 13 millimeters thick. To understand these tracks, we'll start with the two charged particles we already know, the electron and the proton.
This is the checkers game where grandson and granddad will bond. This is the kitchen where
Here is a photograph of a particle track in a hydrogen bubble chamber from the Brookhaven National Lab. Given the direction of the applied magnetic field, electrons will curve clockwise. This is a medium-speed electron arching through the cloud chamber. Since we know the strength of the magnetic field applied across the bubble chamber, we can calculate the particle's momentum by measuring the radius of its curvature. The straighter the path, the faster the particle is moving. Also, remember that accelerating electrons lose energy by radiating photons. This causes the electrons to slow down and their curvature to increase. At these 3 points, we see that stationary electrons in our path have been bumped into motion. These are called knock-on electrons. Because they are moving very slowly, they spiral rapidly to a stop. We see a lot of these in bubble chambers. The track ends when the electron is captured by a proton to form an electrically neutral hydrogen atom. In this bubble chamber photograph from CERN, we see a particle's track rotating counterclockwise. This indicates that it is positively charged. The particle's line is also thicker than the others. This indicates that it is a large, slow-moving particle. This is a characteristic of proton tracks. Now let's take a look at some of the new particles that sent the world of physics into never-before-seen territory. In 1932, Carl David Anderson began investigations into cosmic rays and encountered unexpected particle tracks in his cloud chamber photographs. The 6 millimeter thick lead plate in the chamber is designed to slow particles down. This particle came up from the bottom and is curving counterclockwise, indicating that it has a positive charge. You'll note that its curvature increases after passing through the lead plate. This curvature indicates that its mass is the same as an electron. This was the discovery of the positron. In 1928, 4 years before Anderson discovered the positron, Paul Dirac predicted the existence of antimatter and proposed that all particles had antiparticles, and that they would annihilate each other if they came into contact. The positron is the antiparticle of the electron. This is an example of converting matter to energy.
This is the checkers game where grandson and granddad will bond. This is the
Here's an event in a cloud chamber that shows the creation of a pair of particles, one electron and one positron. This event was the conversion of a high-energy gamma ray that kicked an electron out of an atom and was itself converted into two particles. The gamma ray photon does not show up in the cloud chamber because it has no charge. This is an example of converting energy to matter. The energy of the gamma ray photon had to be as great as the energy embodied in the two particles. For electrons and positrons, that comes to around 1,000,000 electron volts. Any theory that attempts to explain this behavior will need to identify a way for energy at any point in space to create matter.
This is the checkers game where grandson and granddad will bond.
In 1932, Paul Kunz discovered the muon. Using both the direction of the curvature and the thickness of the bubble track, he calculated that it was a positively charged particle that was lighter than a proton, but heavier than an electron. Later on, it was found that this was the anti-muon. Here's another look at a muon created by an event that created two visible particles, a muon and an unknown particle. The muon displayed a new particle property that had not been seen before. It was unstable. Unlike protons and electrons, the muon would only exist for a short period of time before it decayed into other particles. One was an electron, and the other was unknown. On average, it lasted only 2.2 microseconds. That's 2.2 millionths of a second. Muons are light, elementary particles like the electron and the positron. These particles are called leptons, meaning light rather than heavy like a proton. The particle that was created at the start, along with the muon, turned out to be the long sought-after particle called the pion. In 1947, using cosmic rays at high altitudes, this particle was found. Here we see an event that kicks a proton into motion and creates a muon and a pion. Then we see the pion decay into an anti-muon that itself decays into a positron. It lasted only 26 nanoseconds. Now that is a very short life. The muon lasted almost 1,000 times longer than that. Pions are spin-zero particles with around 14 hundredths of a proton's mass. Although that's small, it's a good deal more massive than the muon. Pions came in 3 flavors, one with a positive charge, one with a negative charge, called the anti-pion, and one with no charge at all. Also in 1947, another particle called the kaon was discovered by George Rochester and Clifford Butler. They also used cosmic rays. Here's a look at their bubble chamber picture. Just below the lead plate, in the lower right-hand quadrant, you see an inverted V that extends to the lower right. Measuring the momentum and charges, they determined that they were a pion and an anti-pion. Rochester and Butler concluded that this event had to be a photographic record of a novel phenomenon, the decay of a previously unknown neutral heavy particle, later called the kaon. The discovery of kaons represented the first time we deduced the existence of a particle from its decay components. One of my favorite particles is the neutrino. You'll recall from our segment on radiation that the beta rays were ejected electrons. What's happening here is that a neutron inside the nucleus of an atom is spontaneously decaying into a proton and ejecting an electron in the process. The mass of the proton plus the mass of the electron is less than the mass of the neutron. And because energy is conserved, some energy must be released to make up for the difference. From Einstein, we know that energy equals mass times the speed of light squared. So, if the lost mass is turned into energy, we can calculate the amount. Just under 1,000,000 electron volts per atom. It was assumed that this energy was accounted for by the kinetic energy of the ejected electrons. In 1927, two physicists, C.D. Ellis and W.A. Worcester, set out to measure this energy. They used bismuth-210, a product of radium decay that itself decays into polonium. The rate at which unstable radioactive nuclei decay in a sample is called the activity of the sample. The greater the activity, the more nuclear decays per second. This is rather easily measured with devices like a Geiger counter. Given the number of radiating molecules in a sample, and measuring the activity, we can calculate the probability for any one molecule to decay in a second. This is called the decay constant. We find that the decay constant is always a small number, constant over time, and different for different materials. Both the activity rate and the number of radioactive nuclei vary over time. As a sample decays, the number of radioactive nuclei decreases. With fewer radioactive nuclei, the activity rate also decreases. From this, we get the exponential law of radioactive decay. It tells us how the number of radioactive decay in a sample decreases with time. The half-life is the time it takes for the material and activity to be reduced by half. Bismuth-210 has a half-life of 5 days, meaning it takes 5 days for half of any amount to transform into polonium. We cover half-life in more detail in the How Old is the Earth-Moon System segment in the How Old Is It video book. The experiment was simple. Place the bismuth into a calorimeter. The calorimeter keeps the energy of the beta radiation inside the container. Over the 5 days, each and every ejected electron's kinetic energy is converted to heat as they collide with the water molecules and come to rest in the calorimeter. Measuring the change in temperature allows us to calculate the amount of energy absorbed. The results showed that each bismuth atom naturally emits 0.36 million electron volts. But here we had a significant discrepancy. Conservation of energy and Einstein's equations called for 0.8 million electron volts. That's more than twice as much as was measured. This was a real problem. Niels Bohr thought that the conservation of energy didn't hold in this case, while Wolfgang Pauli thought that it did and proposed that there must be another particle that doesn't interact much with its surroundings and carried away the missing energy. In 1931, Enrico Fermi named Pauli's particle the neutrino, or a small neutral particle. The neutrino's predicted mass was around 1/3 of an electron volt. This is over 1,000,000 times smaller than the electron. Its predicted spin was 1/2, and its predicted speed was almost the speed of light. This would have beta radiation look like this, with both an electron and a neutrino being ejected. This particle was finally observed in a hydrogen bubble chamber captured in 1970. The invisible neutrino enters from the lower right and strikes a proton, where the three particle tracks originate. The proton is kicked into motion, and the neutrino is converted into a muon and a pion by the power of the collision with the proton. The neutrino is a critical component in many nuclear reactions that occur in stars. The detection of solar neutrinos and of neutrinos from supernova 1987A marked the beginning of neutrino astronomy. Today, there are a number of neutrino observatories in operation around the world, and one under construction, to better understand these fundamental but elusive particles. We'll take a closer look at one of them, the Super Kamiokande, located 1,000 meters underground in a Japanese mine. It contains a lake holding 50,000 tons of ultra-pure water, surrounded by an inner detector with over 11,000 photomultiplier tubes that flash when struck by a photon created by a neutrino interaction with the water. The speed of light in water is slower than the speed of light in a vacuum. A neutrino interaction with the electrons or nuclei of water can produce a charged particle that moves faster than the speed of light in water. This creates a cone of light known as Cherenkov radiation. This is the optical equivalent of a sonic boom. The Cherenkov light is projected as a ring on the wall of the detector and recorded by the photomultipliers. This figure shows the Sun as observed by Super Kamiokande. The Sun sends about 65 billion neutrinos per square centimeter our way every second. That's over 400 billion neutrinos per square inch per second. That's a lot of neutrinos. And almost all of them pass right through the Earth and out the other side. Trillions of neutrinos are passing through your body every second. I think that neutrinos will wind up playing a significant role in our understanding of dark matter. In 1969, a team of scientists at the Stanford Linear Accelerator Center, or SLAC for short, in conjunction with MIT, performed scattering experiments similar in principle to what Rutherford did to probe the atom 58 years earlier. Rutherford's target was a gold foil. In the SLAC experiment, the target was liquid hydrogen at a very cold temperature to keep the protons as close together as possible. As a source, Rutherford used a small piece of radium. The energy of the naturally occurring alpha particles was 7.7 million electron volts. Here we use electrons and accelerate them to nearly the speed of light. To do that, we construct a glass tube. Then we connect a negative charge to the entrance and a positive charge to the exit. When the battery is turned off, electrons flow in any direction. But with the battery turned on, the electrons accelerate down the tube along the electric field. To get a really high velocity, we connect more and more of these tubes together. At SLAC, the length of the tube is 3 kilometers. That's 1.86 miles. This creates electrons with 40,000 times the energy than the alpha particles used by Rutherford. This high energy is essential. You cannot probe inside a proton with a large wavelength electron. Remember that the wavelength of an electron in its ground state around a hydrogen nucleus is 200,000 times larger than the diameter of a proton. But if an electron's velocity is large enough, making its de Broglie wavelength small enough, it can. Slack accelerates electrons to greater than 99.999% of the speed of light, creating a wavelength for the electron that ranges from 2 to 200 times smaller than the proton. The scintillator screen used by Rutherford covered the inside of the apparatus. He had to manually note the flash locations as he viewed them through the swiveling microscope. At Slack, we partitioned the scintillator screen into small strips. Each strip has an attached photo element that converts the flash into an electrical signal. This enables the sending of electronic location coordinates to a computer. This is called a hodoscope. With this, we can precisely measure the scattering angles as the high-energy electrons penetrate the hydrogen atom and approach the proton at the center. Slack also introduces a strong magnetic field that will cause the scattered electrons to curve as they pass through. As you'll recall from mass spectrometer and bubble chamber analysis techniques, the measured curvature will give us the momentum and velocity of the electrons. To measure this, a second hodoscope is installed at an angle. At the end of the process, the electrons enter a calorimeter that will measure its energy, much like we just did to discover the neutrino. Putting all these pieces together gives us the complete linear accelerator detector. It weighs 750 tons. The Stanford Linear Accelerator was built to probe the proton with electrons, like Rutherford probed the atom with alpha particles. They both used scattering techniques. These techniques are key to understanding how the Higgs particle was found at CERN in 2012. So we'll take a little time to understand what they found and the principles involved. There are two basic types of scattering. One is called inelastic scattering, where both of the colliding objects change. For example, here we have some of one object's mass transferred to the other at the point of collision. The transfer absorbs energy, so conservation of energy doesn't hold. The other is called elastic scattering, where no parts of the participating objects are changed. Total kinetic energies are preserved, or nearly preserved. In both elastic and inelastic collisions, the conservation of momentum always holds true. Rutherford was examining alpha particle scattering angles off a gold atom target to determine the size of the nucleus. He had to use an alpha particle probe with fixed energy at 7.7 million electron volts. The Coulomb force was repulsive, and his target nucleus was fixed in the solid gold foil. So the target recoil velocity was tiny because the entire foil had to move. The Slack experiment could vary the incoming electron energy up to 17 giga-electron volts. The Coulomb force was attractive, with significant target recoil when a high-velocity electron collided with a target proton. The Slack experiment was designed to examine this transfer of momentum from the electron to the proton at various electron energies and scattering angles to find out if the proton's positive charge was distributed evenly throughout its volume. The physicists controlled the incoming electron's energy and momentum and carefully measured the outgoing energy and momentum for a particular scattering angle. With that, they calculated the amount of momentum lost by the electron. Given the conservation of momentum, the electron's loss would be equal to the proton's gain. Suppose we're counting 10-degree deflections as a hit. A relatively slow-moving, low-energy electron can get a 10-degree deflection far from the center of the proton. This would make the size of the proton look large. In addition, the interaction between the electron and the proton would be weak. We'd find that only a small amount of momentum would be transferred. If we increased the velocity of the electron and kept its distance from the proton the same, it would not be deflected 10 degrees, and the interaction would be considered a miss. An electron with this increased energy would have to approach closer to the proton to get deflected 10 degrees. This would have the effect of making the proton look smaller, and in addition, the momentum transfer would be greater. This gives rise to the concept of cross-section. If we take a look at the total area we are shooting into, and the smaller area that represents the target, we see that the probability of a hit is equal to the target size divided by the total area. You can see that as the target cross-section shrinks, the probability of a hit goes down. Of course, we have a large number of targets in the area, the liquid hydrogen protons, so we add them together to get the total cross-section. Slack calculated the cross-section by controlling the number of incident electrons and counting the hits. Here's a graph of the interaction probabilities against the momentum transfer found by the Slack experiment for electrons with energies below 7 giga-electron volts that scattered by 10 degrees. The closer to the target we get, the smaller the cross-section, decreasing the probability of a hit, while at the same time, the momentum transfer increases with each hit that we do get. The velocity of the electrons remained the same, indicating that no energy was being transferred to the proton. This is exactly what we would expect from elastic scattering. But at incoming electron energies between 7 and 17 giga-electron volts, this dependency changed significantly. In particular, for 3 final proton state energies, the momentum transfer dependence on cross-section was significantly weaker than for elastic scattering. And what's more, the protons absorbed significant amounts of energy from the colliding electrons. Physicists refer to this phenomena as resonance. To understand what's going on, we'll take a closer look at the final proton state. You may recall that Einstein's formula for mass and energy is E equals mc squared, but this only applies to a mass at rest. For a moving particle, the energy-mass conversion includes the particle's momentum. In our case, we see that the final mass of the proton goes up with an increase in energy and goes down with an increase in momentum. If you think of mass as confined energy, what is happening here is that the incoming electron's energy is being converted into increases in the mass of the proton. This is inelastic scattering, and the 3 resonances indicate the proton has 3 internal components. Back in 1964, a quark model was proposed by Murray Gell-Mann and George Zweig to help explain protons, neutrons, and the wide variety of newly discovered heavy particles like pions and kaons and others. The discovery at SLAC in 1969 that the proton has 3 parts constituted evidence that quarks were real. One of the key things to remember about the theory is that quarks are so strongly bound together that it is impossible to study one on its own in order to determine its properties. This means that all we know about quarks is derived from the properties of the particles that bound quarks create. We call particles made of quarks hadrons, meaning heavy. In studying hadrons, we find 2 kinds. Those with 2 quarks are called mesons, and those with 3 quarks are called baryons. All quarks have a spin of 1/2, and the sum of quark charges needs to give us the charge of the hadron. The baryons we've seen so far are the proton and the neutron. Quark theory has it that there are 2 flavors of quarks that make up these baryons called the up quark and down quark. Protons have 2 up quarks with 1 down quark, and the neutron has 1 up quark and 2 down quarks. In order to get the correct charge of the proton and the neutron, the up quark must have a positive charge that is 2/3 the charge of an electron. The down quark must have a negative charge that is 1/3 the charge of an electron. The down quark must also have a little more mass than the up quark for the neutron to have a little more mass than the proton. Note that the sum of the quark masses falls far short of the mass of the baryon. This indicates that there is a lot more going on inside the proton than we've seen so far. The up and down quarks are the lightest and most stable quarks, and all other quarks will decay into these two over time. The two mesons we've seen are the pion and the kaon. The positively charged pion has an up quark and an anti-down quark. The negatively charged kaon contains an anti-up quark and a third kind of quark called the strange quark. It was needed to explain the length of time it took the kaon to decay. In addition to the up, down, and strange quarks, we have discovered the charm, top, and bottom quarks for a total of 6. One of the key rules seems to be that they can only combine in combinations of 2 or 3 as long as the sum total of charge always equals the charge of an electron or a proton or 0. So armed with quarks, physicists intensified their search for some of the 3 quark particles predicted by Gilman and Zweig's theory: the lambda, psi, and omega baryons. In 1947, the lambda particle was discovered. Here we see a V shape with the creation of a pion and a proton. It was the proton that told us the decaying neutral particle, lambda, must have had 3 quarks. The particle was expected to live for about 10 to the minus 23 seconds, but actually survived for 10 to the minus 10 seconds. The property that caused it to live so long was dubbed strangeness and led to the discovery of the strange quark. In 1964, the psi baryon was discovered at the Brookhaven National Laboratory. Antiprotons arrive from the left. One of these antiprotons collides with a hydrogen nucleus, a proton, resulting in mutual annihilation. The mass of the proton and the mass plus kinetic energy of the antiproton give birth to 2 heavy particles, a negative Xi and its antiparticle. Also in 1964, at the Brookhaven National Laboratory, the omega particle was discovered. This is one of the most famous bubble chamber pictures of all. It shows the discovery of this long-predicted particle. In this photograph, we have manufactured kaons entering the chamber on the left. To help see the omega particle, I'll remove all but the tracks associated with the omega event and work backwards from the V on the right that creates a pion and a proton. This is the trademark decay signature for the lambda particle. We also see V's in the upper right and in the lower middle where positron and electron pairs are created. This is the signature for high-energy gamma rays. If we draw lines back to where the lambda particle and the 2 gamma rays cross, we see that a neutral particle decayed into the neutral lambda and the 2 gamma rays. This is the decay signature for the neutral psi particle. We can now draw the path of the psi particle back to the kink, where another particle was decayed into the neutral psi and a pion. Given all the masses, energies, strangeness, and charges involved, this fit the expected properties of the omega particle that's made up of 3 strange quarks. Tracing the path of the omega particle back to the kink in the path of the kaon, we can see the decay that created the omega particle and measure the length of time the omega particle existed. It has a very short life of 82 trillionths of a second. The physicist working on analyzing this photograph was so excited about his find that he woke up the director of the Brookhaven Laboratory in the middle of the night to give him the news. As with other predictions of previously unobserved particles, this discovery gave a tremendous boost to quark theory. Now's a good time to review the particle sizes we've seen so far. In our first segment, we used an electron microscope to see a carbon atom with a diameter of 0.14 nanometers. That's 1,000,000 times smaller than the width of a human hair. In our second segment, we probed the atom with alpha particles and found that the nucleus was very small compared to the atom. Here we have the carbon nucleus at around 26,000 times smaller than the carbon atom. The simplest nucleus is hydrogen's. It's just a proton. At this level, the nanometer is way too large, so we'll move to femtometers instead. There are 1,000,000 femtometers in 1 nanometer. Modern experiments have produced excellent results and show that the diameter of a proton is 1.662 femtometers. In this segment, we probed the proton with high-velocity electrons and found that it contained 3 quarks. Powerful accelerators and hadron colliders have put the upper limit on the diameter of the cross-section of a quark at 0.001 femtometers. That's 1,760 times smaller than a proton and 140 million times smaller than a carbon atom. This is also the upper limit for the cross-section of an electron. The neutrino is the smallest elementary particle, with a cross-section that is 1,000 times smaller than an electron or a quark. That makes it 140,000 trillion times smaller than the diameter of a human hair. When confronted with a vast number of observations, a first step to understanding is categorization. We try to find the similarities and differences between things. When it comes to elementary particles, we have already made some distinctions. We have the small light particles, like the electron and the neutrino, called leptons. And we have the quarks that make up the heavy particles, like protons and neutrons, called hadrons. Everything we see around us is made of these 3 stable elementary particles: the electron, the up quark, and the down quark. A particle's spin is another key distinction that helps us categorize all these particles. You'll recall that electrons and quarks have spin 1/2 and therefore follow Pauli's exclusion principle. Photons have spin 1 and do not follow the exclusion principle. The statistics that describe spin 1/2 particle behavior in large groups was developed by Enrico Fermi and Paul Dirac. They are called fermions, after Mr. Fermi. The statistics that describe spin 1 particle behavior in large groups was developed by Satyendranath Bose and Albert Einstein. They are called bosons, after Mr. Bose. You can imagine that large groups of particles that can't fit into the same quantum state will behave differently than particles that can. In an energy well, the bosons all sit in a condensate at the bottom. The fermions arrange themselves in a hierarchy, like electrons in an atom. For example, a beam of photons can be made to have the same quantum state. This is how a laser works. On the other hand, the inability of electrons to fit into the same quantum state creates an outward pressure that halts a star's collapse and creates white dwarfs. In this segment, we also covered the muon, a higher energy version of the electron. At even higher energies, another electron-like particle called the tau was discovered in 1975. When these leptons decayed, their neutrinos were slightly different. So we have two additional neutrinos, the mu1 neutrino and the tau neutrino, to go along with the ubiquitous electron neutrino. Experimental evidence indicates that decay rates for these particles are different. We have the Gen 1 particles that are stable. They do not decay. In addition, we find that Gen 2 particles decay slower than Gen 3 particles. This gives us one more organizational category to go along with the heavy versus light and the integer versus non-integer spin. So here we see the beginnings of the standard model of particle physics. We'll finish developing this model in our final segment on the Higgs boson.
So, there you have it. Science, ladies and gentlemen, science. I challenged Mr. Batman to come and have a chat about this. I guarantee you he wouldn't know where to begin. He'd even say that is bullshit. He'll even say that that is all made up or something like that. That's how silly. Anyway, these past 45 minutes are enough to debunk the concept of a creator. Mr. Batman, you say, where does information come from, sir? Where does information come from, sir? Well, Mr. Batman, you got to figure that the neutrino, proton, and electron are elementary particles. And of course, they're made up of smaller particles, but they're all just charged particles one way or the other, or they're antimatter. But there's no way for information that you say is passed along by God through all this, through the atoms. There's no way for them to actually do that if you understand what these particles are and how they work. So, Mr. Batman, you are not a science teacher. You are a liar. You are you're very arrogant, full of yourself, and also really, really ignorant. You are not well read. You are not educated. You have read one book your entire life, and it is a book of fairy tales and magic and promises and lies and unfulfilled promises, and it's just nonsense. So, Mr. Batman, you're more than welcome to come on to a debate, not a debate necessarily, but a chat room, an open chat room. And until I get my computer sorted out, I'm going to use Meet for short ones, short open discussions. I've made that decision, and you are more than welcome to come in. I actually want to test that using, instead of Jitsi, I'm going to use Google Meet, and I'm going to test it soon. And see if the restricted time, whether it's 40 minutes or 45 or 60 or whatever, is enough for a discussion. So, having said that, I will thank you very much for watching. You are the best because you watch my stuff. Thank you so much. I do say that this will be the end of this segment. We are atheists. I am creating atheists. Thank you so much for watching. We'll see you in the next video. Thank you so much for watching.